In example 2, we're going to see a classic tension and pulley problem. So we have this 8-kilogram box that's on top, resting on a frictionless surface, that's tied by a cord which hangs over a pulley, which you can see in the diagram here. It's tied by a cord to a 1-kilogram mass that's hanging below. And it's a frictionless, massless pulley. What that means is that there's just going to be no resistance to this in this pulley that's going to resist any of the other forces in this problem. And that's going to be the case for any pulley that you're going to come across in Physics 11. If you're not told that it's frictionless and massless, you're safe to assume that it's frictionless and massless. But in this case, we're told right off the bat. And we're asked to find the acceleration in the system. So we have to think about which direction the system is going to accelerate. And one of the easiest ways to do that is to think about or to examine the free body diagrams. So let's consider mass 1, the mass on top, and we'll call the hanging 1-kilogram mass, mass 2. So I'm going to start by drawing the free body diagram of mass 1. So mass 1 has a gravitational force downwards, Fg. Because it's resting on a surface, it's counteracted by an equal and opposite normal force upwards. And it's being pulled to the right by the tension in the rope. And with no friction or any other external force, these are the only three forces that could possibly be acting on this block. So from this diagram already, we can see that mass 1 is going to accelerate to the right. Now, just like the forces that we saw in example 1, with systems that are tied together by ropes, where you have these tensions involved, the whole system has to accelerate together. So this means that if the block on top is accelerating to the right, the rope is going to be pulling around the pulley, which means that block 2 is going to be accelerating downwards. So that sets us up, that gives us an intuition for what we should be seeing in the free body diagram of mass 2. So here's the dot representing mass 2. It'll have a force of gravity downwards, which should be smaller than the force of gravity acting on mass 1, because mass 1 is larger. And it also has a tension force acting upwards. It's the only other force. There's no normal force because it's not resting on a surface. The only other possible force acting on mass 2 is the tension force. Now, because these tensions are coming from the same source on the same rope, just like in the last problem, they must be equal. The tensions along any one given rope are going to be equal. And because we know that the system is accelerating downwards, that's the direction of the acceleration, means there must be a net force downwards. So the force of gravity on the 1-kilogram mass must be larger than the tension force, so that there's a net force downwards, which is going to cause an acceleration. So you can see that this tension is actually acting in different directions for each block. It's acting to the right for the mass 1 on top, and it's acting upwards for mass 2. So what that means is that the pulley redirects the tension. It's still the same rope, so the tension is still equal for acting on each mass, but they're acting in different directions because that tension has been redirected by the pulley. So what we're going to do is we're going to simplify this problem. Now that we know that the pulley is just redirecting these forces, we're actually going to redraw the scenario without the pulley at all. So if block 1 is being pulled to the right, so it's accelerating to the right, and block 1 is being pulled by gravity downwards, so its acceleration is downwards, what we're going to do is we're going to draw this problem where we have those accelerations acting in the same direction. So here's block 1, on a frictionless surface, and what we're going to do is we're going to tie it to block 2, and now we can think about these tensions as acting equally and oppositely on one surface together. So M2 is still being pulled. It's being pulled by the force of gravity, but now in this scenario where we have removed the pulley, instead of M2 being thought of as pulled down, we're going to draw it as though it's pulled to the right. So it's weird to see Fg acting to the right, but you can think of it as it's an equivalent to an applied force. We're just simplifying the problem so that we can set up an F-net equation that's easier to see. Well, now that we have the system drawn like this, it's actually pretty clear to see that the net force acting on this system, the only force acting to the right is the force of gravity acting on mass 2. And we also have the two tensions acting to the right and to the left, but again, just like we saw in example 1 previously, those tensions are like an internal force that don't affect the net force of the system. So it's actually a pretty simple F-net situation, and we can go ahead and say, because this is for the whole system, I should make this clear. It's an F-net statement for the entire system, so this is the mass of the whole system times the acceleration of the whole system is equal to Fg, and this is just on mass 2, so this would be mass 2 times g, the acceleration due to gravity. And we can rearrange this equation nicely. m2g divided by the mass of the system, and the mass of the system is just going to be mass 1 plus mass 2. All of these are known values, so we can go ahead and plug these in. Mass 2 is 1 kilogram, g is 9.8, divided by m1 is 8 kilograms, plus the 1 kilogram of mass 2. So the acceleration is 9.8 divided by 9, and that gives us an acceleration rounded to 3 significant figures of 1.09 meters per second squared.